Hi, I am Michael Varela, and I will be going over the research paper Nautilus Fishing for Deep Bugs with Grammars. Here is the here is the table of contents, and I will be going over 1, the introduction, 2, background, 3, challenges, 4, design of Nautilus, 5, implementation, 6, evaluation, 7, related work, 8, limitations, 9, future work, and 10, conclusion. Now I'm going to start off with the introduction. Software and programs are used everywhere in today's world. And we need a way to test these programs in ways that we, the developers, wouldn't expect. Fuzzing allows us to feed these programs huge amounts of inputs in order to hopefully find security vulnerabilities and trigger crashes or unexpected outputs. A common fuzzer is called a general purpose fuzzer, and although these are good, when they encounter highly structured inputs like JavaScript or PHP interpreters, the input needs to be perfectly correct and formed in order for the program to even run. A common way that fuzzers will generate input is by flipping bytes and doing random mutations. But this leads to this problem where sometimes you get a valid input. Coverage-driven fuzzers allow the fuzzer to get feedback on if it's covering more or less code, which would hopefully get the fuzzer closer to finding a security vulnerability or a crash. Now I can introduce Nautilus, which bridges the gap between context-free grammars, which I will talk about, and code coverage feedback in order to make improvements on the current fuzzers that we use today. Nautilus has real-world impact. Nautilus found many bugs in programs like PHP, mRuby, Microsoft's Chakra core, which brought in over 2,600 in bug bounties, and outperformed current fuzzers by orders of magnitude. Section 2, background. There are currently 2 primary methods to generate test cases for a fuzzer: mutation-based and generation-based. Mutation fuzzing takes a supply of seeds, which are inputs, and modifies them using operations like bit flipping or splicing multiple seeds together in order to get the input that it then uses on the target program. Generation-based fuzzing creates inputs from scratch based on a specification or grammar of the programming language, which ensures that the inputs are syntactically valid. A lot of modern fuzzers use code coverage, so they can tell which inputs are bringing them to new parts of the program that the previous did not. But traditionally, grammar-based fuzzers have lacked this feedback mechanism. To understand Nautilus, you need to look at context-free grammars. Context-free grammars are a set of production rules for the language. Terminals can be broken down further and further. Non-terminals are where the breakdown stops. The grammar describes the syntax of the programming language and shows what is valid and not valid. The strings that are generated by the context-free grammar can be represented as a derivation tree. Nautilus utilizes these derivation trees and makes internal changes to the tree for inputs rather than making changes to the raw text strings. Section 3, challenges. There are 4 main goals and challenges that Nautilus had to overcome for it to be an effective fuzzer. The first goal is generating syntactically and semantically valid inputs. The problem is that the amount of possible inputs is a lot larger than the number of valid inputs that the program will accept. Goal 2 is to have the fuzzer be independent from a starting seed pool. A lot of coverage-driven fuzzers need an initial seed pool to start the fuzzing process. Goal 3 is having high coverage of the target functionality. In order to get high coverage, you need to be successfully passing the initial input checks and have a semantically and syntactically valid input. You also need to be exploring new and unseen execution paths that your fuzzer has not been to. Goal 4 is good performance and speed. Having fast testing cycles are crucial for a fuzzer's overall effectiveness. To keep a high execution rate, the generation method of inputs must be fast and small. Nautilus is designed to address these 4 goals by combining grammar-driven fuzzing with feedback-driven seed generation. 4. Design of Nautilus. The image on the slide is the workflow of Nautilus. Nautilus starts by parsing the user-provided grammar and generating 1,000 initial random inputs from scratch. These inputs are then executed in the instrumented binary, which checks for new code coverage. If an input triggers new coverage, the scheduler minimizes the input in order to keep it efficient and fast, and then adds it to the queue. The scheduler decides whether it wants to generate new inputs or mutate and change the existing ones from the queue to explore deeper code paths. Unlike most fuzzers that mutate raw bits randomly, Nautilus operates by changing the internal derivation trees of the grammar, which ensures that these mutations are following the rules of the grammar and keeps the inputs syntactically and semantically valid. Nautilus uses 2 generation strategies to modify the inputs. There is naive generation and uniform generation. Naive generation is Nautilus randomly choosing a rule when going down the parse tree, which then acts as the structure to generate the new input off of. Uniform generation is when Nautilus draws the trees uniformly from the set of all of the possible trees of a specific length that it can generate to avoid the structural bias. In order to keep Nautilus fast and effective, Nautilus uses 2 main minimization techniques: subtree minimization and recursive minimization. These both act as a way to reduce the input size of the seed, maintain the coverage of the original seed, and speed up the execution as a whole. Nautilus uses a wide variety of mutation methods in order to generate new seeds from the interesting ones that it found earlier. Random mutation replaces a random node in the parse tree with a newly generated valid subtree. Rules mutation is Nautilus replacing nodes with subtrees generated by other possible rules within the grammar. Random recursive mutation is Nautilus targeting nested structures by repeating a recursion within the tree to stress test the limits of the program. Splicing mutation takes 2 successful inputs, takes their subtrees, and combines them to make a new interesting seed. Nautilus also uses a AFL style bit flipping mutation, which a lot of other fuzzers do as well, which flips random bits. In order to handle non-context free languages, Nautilus uses unparsing scripts. These allow for arbitrary computations that cannot be covered by normal context-free grammars. A good example of this is XML opening tag that needs to have a closing tag at the end, but a simple context-free grammar cannot convey this. 5. Implementation. Nautilus is implemented using Rust. Rust's low-level control over hardware and memory allow it to be efficient, similar to many current parsers. In order for Nautilus to provide code coverage feedback for each individual seed, the target application is compiled with a custom compiler pass-through. This instrumentation shares a bitmap with the application in order to track the basic block transitions in order to tell what is covering new code. Nautilus utilizes a fork server mechanism. This allows it to run the seeds on the target application in a highly efficient way, which allows it to test more seed inputs in a shorter amount of time. Nautilus supports grammars in both a JSON format and ANTLR format. By supporting ANTLR, Nautilus can use over 200 existing publicly available grammars. The fuzzer has many phase states for the seeds that are being tested. When the fuzzer finds a seed that covers new code and is interesting, it marks it as such and puts it in the queue. Every interesting seed goes through a couple different phases of testing. There's the initial state where the fuzzer is trying to simplify the input as much as it can while keeping the same behavior, which increases the efficiency. Then there's the phase where the fuzzer is making very specific changes, such as turning a plus sign to a minus sign to see what happens. Then there is also the random changes it can make. Nautilus keeps rotating through this queue in order to keep moving around and trying as many different things as it can while still making progress on generating more and more interesting seeds. If in the end the seed never became more interesting, the fuzzer removes it from the queue. 6. Evaluation. Researchers tested Nautilus on 4 widely used scripting language interpreters: mruby, PHP, Microsoft's Chakra Core, and Lua. Nautilus found bugs in all 4 programs. In total, 13 bugs were found, leading to over $2,600 in bug bounties. When comparing Nautilus to other competitive fuzzers, such as AFL and iFuzzer, Nautilus showed superior branch coverage. As an example, in PHP, Nautilus found 10 percentage points of additional coverage compared to AFL. Now the question is, why was Nautilus so efficient and successful at finding bugs? What was crucial to Nautilus's success? The first was Nautilus's feedback and code coverage. Most grammar-based fuzzers do not have code coverage. However, Nautilus does. To see how much of an impact the feedback had on the efficiency of Nautilus, the researchers tried a no-feedback version of Nautilus. They found that Nautilus with feedback or code coverage found more than twice as many new branches as the non-feedback code coverage fuzzer, thus proving that combining the grammar with the feedback and code coverage is one of the keys to its performance. Nautilus's use of splicing was also a huge plus for why it was so efficient. Nautilus was splicing by taking 2 interesting seeds from the queue and combining their trees and forming a new seed to then try. While minimization methods and generation methods that Nautilus used were very effective at the start, they tended to taper off and become less effective as time went on. However, after a couple of hours, splicing and random mutation together accounted for more than 50% of the newly identified paths. 7. Related work. Most fuzzers can be put into two categories: the mutation-based approach and the generation-based approach. The mutation-based approach is very fast and is guided by coverage. However, they lack the grammar knowledge needed to verify the seeds are valid within the grammar of the program. The grammar-based approach is good because it verifies that the input seeds are within the grammar. However, they generally do not have feedback and code coverage built within it. This is where Nautilus differs. Nautilus does not require an initial seed pool. It starts off with some based on whatever the grammar of the target program is. It grows its own semantically correct seed pool, guided by the code coverage and feedback that it gets with each run of a seed. This ensures that it's making progress towards covering the overall code and branches in the program. This helps identify bugs that normal traditional fuzzer methods miss. 8. Limitations. Like many coverage-guided tools, Nautilus currently requires source-level access to the target application in order to add the instrumentations for feedback and code coverage. Without this access, Nautilus wouldn't be able to give feedback, which would dramatically decrease the efficiency of Nautilus. While Nautilus does not need an initial seed pool, it still requires a grammar in order to function. In many cases, the user needs to come in and tune this grammar in order for it to run the best. Nautilus supports scripting for non-context-free languages. However, for some tasks, say such as file offsets, it is still very difficult. There can be many unknowns in a non-context-free grammar, so solving this problem is difficult. Nautilus generates syntactically valid seeds. However, with generation-based approaches to fuzzing, ensuring things such as a variable being defined before it is used is a difficult task when doing different mutation techniques. There is also a lot of manual work that goes into preparing the context-free grammar itself. For example, you might have to shrink some of the literals to prevent the fuzzer from wasting time if it's not an interesting seed. 9. Future work. Right now, Nautilus requires the source code of the target application in order to fuzz. The instrumentation-based backend could be replaced with an AFL Q-EMU mode backend. This would essentially allow Nautilus to fuzz targets where it does not have access to the source code. This would make Nautilus much more versatile in which programs it can effectively fuzz. Some of the manual effort that is needed to add important symbols, identifiers, or class names into the grammar can be reduced. In the future, this could be automated by using strings that Nautilus gets from executing seeds into the grammar. The handling of non-context-free grammars can be improved by adding labels. Nautilus can use these labels to determine specific places and know when to do certain things. Lastly, the researchers behind Nautilus can explore other generation methods. Them exploring context-free grammars with feedback help them create Nautilus, which is a very efficient fuzzer. More exploration could mean better efficiency. 10. Conclusion. In the end, Nautilus shows that leveraging grammar and feedback, fuzzing can be enhanced and efficient, even with highly structured input. Having feedback, along with a grammar-based fuzzing approach, improved code coverage by at least a factor of 2 across all target applications, including mruby, PHP, Chakra Core, and Lua. This is real-world impact, finding bugs in real applications that was awarded over $2,600 in bug bounties during the evaluation. Nautilus, as a fuzzer, provides efficiency and performance, leveraging context-free grammars and feedback that can only get better and more efficient with more time and testing. Thank you.